Good morning, good afternoon, and good evening, ladies and gentlemen. And in today's video, we're going to look at holes and asymptotes. Now, these only really apply in most cases when you have rational expressions. So there are two types of asymptotes. We're going to talk about the asymptotes first, and we're going to talk about the holes. So first, we're going to talk about horizontal asymptotes. Okay. Now, when we talk about horizontal asymptotes, let's take a look at this. So let's say we have three different equations, and let's say I have here x squared plus 3x plus 2 on the top, and let's say x squared plus 2x plus 3 on the bottom. And then here we're going to have x plus 2, and on the bottom we'll have x squared plus 3x minus 2, and on this third one let's have x squared plus 2x plus 3, and on the bottom let's have x plus 2. Okay, now your first step when you want to find horizontal asymptotes is to select term highest degree in the numerator and denominator. All right, so highest degree, well, over here we see we have an x squared. On the bottom we have an x squared. Those are both the highest degrees. Over here we have x, which is the highest, and x squared. And over here we have x squared, and here we have an x. So when we take them, we're going to separate them from everyone else. Just forget that these are here. So you have x squared divided by x squared. Over here you have x divided by x squared. And over here you have x squared divided by x. Now, when we do this, you're going to notice that I have an x squared divided by an x squared. Well, x squared divided by x squared, that's just 1. Now, to put this in a little bit of perspective, let's say I put a 3 there and a 2 there. So let's say it was 3x squared and 2x squared. Well, the x squareds are still going to cancel out, but in this case it would give me 3 over 2. So whenever you want to find asymptotes, you're basically asking yourself, what happens as x approaches infinity or negative infinity? So basically, as x gets bigger and bigger and bigger, both positively or negatively. Well, in this case, no matter how big or small x gets, the answer is still going to be 3 over 2, or 1. I guess you could say 1 over 1. So this means that if the numerator is equal to the denominator, which it is in this case, because you can see our degrees in this case are both x squared. So they have equal degree. So if they have equal degree, then the horizontal asymptote is at the ratio of the coefficients. So that's rule number 1. Let's see what happens in this case. X divided by x squared. Well, in this case, this x is going to cancel out. One of these x is going to cancel out, and I'm going to be left with 1 over x. Well, so what happens as x goes towards infinity? So when I say that, that means x is getting bigger and bigger and bigger. So 1 divided by, let's say, 10. Well, that's 0.1. 1 divided by 100 So I'm going to write this here. 1 divided by 100, 0.01. 1 divided by 1,000, 0.0001, and so on and so forth. 1 divided by a million, and so on. What am I noticing is that my answer is getting closer and closer and closer to 0. So the second rule would be, and in this case you notice that my numerator was less than my denominator. And you'll notice that because on the top I had a 1, on the bottom I had a 2. So my numerator's degree was less than my denominator's degree. So in this case, the horizontal asymptote would be 0. Because as you get closer and closer, bigger or smaller, you're going to get closer and closer to 0. And lastly, we'll look at what happened in this last case. And in this last case, you have x squared divided by x. Well, this x cancels out with one of these, so you're left with x. Now, as x goes towards infinity, so as x gets bigger and bigger and bigger and bigger and bigger, it doesn't really matter because there is no more fraction here. So because there's no more fraction, there is no horizontal asymptote. So in this third case, where the numerator was bigger than the denominator, because you could see here that my degree on the top was 2 and my degree on the bottom was 1, so the degree on the top was bigger than the bottom. There is no horizontal asymptote. And that is the 3 rules of horizontal asymptotes. They apply in any situation. Next up, we'll talk about vertical asymptotes. Now, next up, when we talk about vertical asymptotes, let's use this example here. So let's say we talk about 1 over x. So once again, a vertical asymptote, as you get closer and closer to 0. Now, when we say vertical, that means now you're looking at the y. And the y values here, well, what is it never going to touch as you get closer and closer? Well, you're never going to touch 0. Because in this case, you will never get So the vertical asymptote always comes from the restriction. So vertical asymptote restriction of the rational expression. So in this case, x cannot be 0. Let's say I had 1 over x plus 2. In this case, x cannot be negative 2. So these are both vertical asymptotes. What does that mean for my graph? Well, let's take a look below. So this is my rough graph here. Now, let's say we're looking at 1 over x. Well, as we learned from the last page, my top is 1, my bottom is an x. So I can say that the exponent of the bottom is bigger than the top. Why? Because there's no x here. And if there's no x here, I can assume this is something like x to the power of 1. Because, as we know by exponent rules, x to the power of 0 is 1. So I have a 0 on the top, I have 1 on the bottom. So I know the exponent of the bottom is bigger than the top. So numerator is less than denominator, which means I should have a horizontal asymptote at y is equal to 0. And that's how we name it. We say y is equal to 0. So y is equal to 0 is a horizontal asymptote. Now, I also know x cannot be equal to 0. So we name it x is equal to 0. What does this basically mean? This means that as my function gets closer and closer to 0, it flies away. It can't touch 0, both for your x and for your y. Same thing from the left side. Now, what happens if I go 1 over x plus 2? Well, it's the same situation. You have a horizontal asymptote at 0 still, because the top is still smaller than the bottom. But now I have a vertical asymptote at negative 2. So let me go 1, 2. This means that I'm going to use different colors here. So this is my vertical asymptote at x is equal to 2. This means I cannot touch 2. Can't touch it at all. I also can't touch 0 for y. So how's this graph going to look? Let me put this in white. So I can't touch 2, can't touch 0, so it's going to look like this. Can't touch 2, can't touch 0. So that would be how 1 over x plus 2 looks. So let's see what a hole is then. Alright, so at long last, what is a hole? Well, let's take this example here and let's do what we normally should do, which is to factor, so we can find our restrictions. X minus 2 over x plus 2, x minus 2. Now, mind you, if you're looking for your horizontal asymptotes, you want to look at your original function, which is this. You're going to take your x, you're going to take your x squared. So I know that my top is smaller than my bottom. So numerator is less than denominator, so I know my horizontal asymptote is at 0. Now, I have my restrictions here, so I know x cannot be negative 2 and 2. So that means I have a vertical asymptote at negative 2 and 2. But here is where the rub happens. Now, of course, you have an x minus 2 on the bottom, you have an x minus 2 on the top, so you have a final equation of 1 over x plus 2. Look familiar to the equation I had on the other page? Well, it should. And that's because they are identical. Now, what does this mean for a hole? Where are you going with this? Well, what's the difference between a hole and a vertical asymptote? Well, a hole is made from a restriction that cancels out. And as you could see, x minus 2 was one of my restrictions, which gave me the x cannot be 2. But it canceled out. So how do I find a hole? Well, you take that value and sub into the simplified equation. So I know that x minus 2 cancels out. What belonged to x minus 2? Well, that was this 2 here. So we're going to sub 2 in here. So 1 over 2 plus 2 is 1 over 4. This means I have a hole at 2 and 1 over 4. So how would this look like in a graph? So let's graph this out. This would mean, sorry, I'm going to have to put it in this very tight space here. Alright, so normally I should have a horizontal asymptote at y is equal to 0. And I should have a vertical asymptote for sure at -2. So -2. And I know I have a hole, not a vertical asymptote, a hole. I'm going to use a different color for that. 1, 2, at 2 and 1 over 4. 1 over 4 is 0.25, so let's say this is 1. 0.25 would be somewhere around here. So what do I mean by a hole? Well, this basically means, so let me draw this out first. I can't touch. I'm not worrying about my y-intercept right now. Worried about that when we make the graphing video. So can't touch 0. Can't touch -2. Can't touch -2. Can't touch 0. So flies away. Now, what does this mean for the hole? Well, we'll do a little erasing here. At 2 and 1/4, which is 0.25, you should have what they call a hole. So instead of a shaded in dark, you have a hole. So obviously there is a solid dot and an open dot. You would have an open dot there because it is undefined there. And that is the difference between a hole, a vertical asymptote, and a horizontal asymptote. I hope you understood, and please let me know if you have any questions. Thank you.